Well, welcome everyone to the second session today, and thanks to everyone who stayed on from the first session and the new entrants to the second session for joining us today. Our second session is going to focus on data curation using large language models, and what we'll do is we'll start off with a short and very high-level artificial intelligence primer just to get everybody on the same page about terminologies that we'll use or the domain uses on a regular basis. Then we'll have a few examples to show what Sage has been doing with the large language models, how we have been applying them in various use cases. And maybe some of those use cases would be interesting and useful to you as well for your own applications. And then again, like the first session, we'll have a work session at the end of this second session, which will have specific curation exercises, and we'll all, Christina, Robert, and I will help you out with any questions that you might have for that session. All right, so let's start with understanding AI on a very, very high level. And I realize that many of you are already very familiar with this, so this might be a very familiar information to you, but just to get everybody kind of on the same page about the various terminologies, let's start with a high-level definition of what are AI, ML, deep learning. So AI, or artificial intelligence, as you are probably hearing all the time, are computer programs that are programmed such that they can use information to imitate human behavior or human intellect. Now, a subset of artificial intelligence is machine learning. These are specific programs that are used to learn from data. So they need a lot of data to learn from. And they generally use statistical algorithms in the background to extract information from the data that is provided to them. So that's machine learning, learning from the data. Now, an even smaller subset of that machine learning is called deep learning, which is a very specific kind of machine learning where it uses a specific architecture called neural networks to learn from the data and provide outputs that are more relevant. All right. Now, in the past few months and years, past year and a few months, I think you all have become very, very familiar with the term called generative AI because of the really strong pace that domain is going forward with. So generative AI is another subset of this machine learning, which uses a deep learning based method to generate outputs that are relevant to prompts that are provided to that computer program. And there are various different kinds of generative AI. There is text generation, image generation, music generation, video generation, and voice and speech and code. And all of these different kinds of AI are basically classified by the kind of data that comes out as output from these programs. So if it is text-based, so it's taking in input as text data and providing output as text data, it's text generative AI. One thing to note here is that generative AI is moving at a very, very fast pace. So just an example. This is an example of video generation only like about a year and a half ago where the prompt is Will Smith eating spaghetti. And you can see that the video is kind of clunky, really. Now, only about earlier this year, now these programs are so advanced that they can provide videos like these three, which are much more realistic and sometimes hard to tell whether it's generated or actually shot. Another example of generative AI, especially in the music world, is an example that I'll show here. And what you'll see here is a video of a program generating music based on an input prompt or a question that was given to the program of generating music based on a short sentence. So here, the prompt that was provided is, "It started to sing," and there was an additional information given about style.
We were having fun, programming young, dreaming that one day we'd make it work. Lines of code we'd write all night, hoping that one day we'd get it right. Can we teach the machine to sing? Can we teach the machine to dream? And then, ooh, it started to sing. No, this can't be real. It's just a machine, but the melody, ooh.
Oh, so sorry to cut you off, but that's a song that came up from just a short prompt of "It started to sing" and some additional information of what genre of music that the program should focus on. So that's pretty impressive. Now, obviously, these are really, really fun examples of how this domain is going forward in like an amazing pace. But for today's short session, let's focus on text generation. So here, these are examples of programs where text is provided as input. So you have a short prompt of a sentence of what you want a program to do, and the program outputs a coherent output in text. So it could give you a paragraph based on the question you asked. It could give you other forms of tabular data or other examples of text-based data that it generates from the prompt that was given. Some examples of the models, and you might be very familiar with these names already, are GPT-4o, Llama 3, Claude, and so on. So just to go a little bit more into large language models, so these are generative AI deep learning based models, which have been trained on a large amount of text data scraped from the internet, so that all that training and all that exposure to that data has led to the program be able to read, write, and understand the rules of grammar of human language. And that's how it generates outputs that are coherent paragraphs or coherent sections of data based on the question you ask. So on the top right here is a very generalized structure of what a deep neural network looks like, and these are just building blocks of how those large language models came about. Now, these are some examples or names of large language models that are available today. So GPT-4o, Mistral, Llama 3, Claude 3, and others. What I want to emphasize is that while these all started as language models, so very much text-based, these are very, very quickly starting to take in data that is more than text. So it can take data and pictures and provide you output in terms of data, pictures, and videos, or music, as you heard. And quickly they are morphing into multimodal models in addition to being language models. All right, so a few last bits on large language models before we go into examples of how we are using it. There are a few terminologies that might come up as you get more and more acquainted with large language models, and we wanted to just give you a preview to those. So one is zero-shot learning. So what is it? Let's say that you have, let's take ChatGPT as an example. Let's say you ask ChatGPT a question out of the blue, and it provides you with an answer. How does it do that? That's an example of zero-shot learning, where it basically bases its answer based on the data that is already, it had access to during its training. So it doesn't need any additional information from you. It uses the training data that it already has, and without any additional help, it can provide you with a coherent answer. Second thing that we might hear of is few-shot learning. In this case, what you could do is, to the same GPT, you could provide some examples in addition to the question that you asked. And what it does, in addition to the training data that it already had access to, it uses those examples that you further provided, learns from those examples, and provides you with an answer that is much more catered towards your question. And that's an example of few-shot learning. So for example, if it already has access to few cats and dogs images, but if you provided it with some example images of specific cats and specific dogs, then you could ask more nuanced questions, and it would be able to answer those. So that's an example of few shots. So you give it a few shots at learning new data. The next concept is prompt engineering. I imagine that all of you have already heard about it, or at least have come across it in many aspects. So what is prompt? Let's first start at that. So the question that you ask ChatGPT, that question is your prompt for the model to figure out what the output should be. Now, these prompts can be as generic or as specific as you want it. The more generic prompt would still help the model provide you with a relevant answer, but it might not have a lot of details that you're looking for. So for example, you could give a prompt saying, can you write a short story about a futuristic brave knight? That's a pretty good prompt, but it's a pretty general one. So it will give you a story, but it might not be exactly what you're looking for. Now you could add more details into your prompt or engineer the prompt in a way that it makes it more specific to exactly what you're looking for. So an example would be the second prompt here. Can you write a short story about a brave robot knight? The knight has a name, so a researcher, and you have a specific incident that you want the story around. So that's an example of an engineered prompt where you're providing the model with a lot of information of exactly what you're looking for so that it can provide you the most relevant and more accurate output that would be more helpful. All right. The next one that you might have heard is called retrieval augmented generation. Now this has become very, very popular because it is a very powerful technique that can be used with these large language models to provide information that is much more accurate, much more tailored to your question at hand. So what does it mean? So the models already come pre-trained with a lot of data, but what you can do is you can provide it additional relevant text or data and make a knowledge base for that model to learn from again. And what it does, using this retrieval augmented generation technique, is that it will focus on the new information that you have provided it, the new knowledge base, and it would extract information specifically from that knowledge base to provide you the correct, the more accurate version of an answer. So, for example, the LLMs today, they were trained on data that was until 2020, so they are not aware of what went on today. Like, they don't know the news of today. So, but if you provided a specific information about the newspaper, like a PDF version of the newspaper to the model today, and ask it about an event that happened today, it would be able to give you that answer by retrieving information from that specific knowledge base that you have now provided. All right, so all of these, the concepts that we talked about can be used to make the LLMs much more useful and their outputs much more accurate and catered towards your needs. But these can vary in complexity. So for example, prompt engineering, like just changing the details of the prompt, is probably the most easy way to get the model to do what you want and provide the output that you're looking for. So that is a low complexity, high reward kind of situation. And on the other hand, or the other end of the spectrum, is pre-training the LLM from scratch. So you provide specific information about your use case to the model and train the model again to understand and retrieve information from the data that you want to look at. Of course, that is a much more complex, much more compute-intensive way to do the model, and there's only probably few companies in the world which can do it today. So you could have a whole spectrum of different techniques that you could use to make the LLMs and their outputs much more useful for the use cases. All right, so these are some of the concepts to keep thinking about, to keep in mind as you work through LLMs and use them for your use cases. So with that, I will hand it over to Christina to talk about some of the use cases that we are using the LLMs for.
Thank you, Janita. Good morning, everyone. My name is Christina Conrad. I'm a biomedical data manager at Sage. And this next portion is going to really relate to how we're using LLMs with the NF data portal. And so just to get started, some example use cases of how we at Sage use LLMs can be for data extraction and formatting, adding descriptive metadata, summarizing scientific text, data curation from literature, and then text simplification and translation, and code development. So what I'm going to highlight is the challenge in finding tools for research. And so the problem that I'm sure a lot of you face is understanding what tools to use. And by tools, we're talking about animal models, cell lines, genetic reagents, antibodies. And it's hard to know, what's good, what's used out there, when are there, changes to the most popular animal models. And so the overarching goal that the NF data portal has is to curate this information and provide a single place that people could go eventually and look at what tools are being used and where is the data associated with that tools. So that's the vision. And what want to highlight a few different, challenges that in order to achieve that vision. So one of the challenges is that there's already a lot of information out there. Here's a list of a lot of different tools that are, not to say tools again, so a lot of different locations that you can find information on cell lines, antibodies, genetic reagents, et cetera. And so what we're trying to also do is link a lot of this information to the portal. So we don't need to recreate everything from scratch, but how do we kind of condense this information and make it easier for everyone to understand and find what they need? So here's a list of some of the challenges that might resonate with you. So researchers have to visit multiple databases to find tools for a particular experiment. It can be hard to keep track of changes that occur in the literature. NF is a rare disease, so there's specialized tools. There's not typically a place that people go and publish their unpublished data. A lot of times, that just never gets out there. So there are valuable observations, when things don't work out that potentially should be captured. Another area is that researchers that are new to NF might not have prior knowledge to where to even get started in the lab with NF-related tools. And all in all, to address these challenges, we have built the NF Research Tools database. And it is called NF Research Tools Central. You can find it on nf.synapse.org, and if you click on the upper left, browse tools. And what's there is you'll find cell lines, animal models, antibodies, genetic reagents, and biobanks. So our approach at Sage is we want to build a user-friendly web application, and so that's what we have done, and I'll go into a few of the different elements here. So when you get to the home page, you'll see this, NF Research Tools Central, a little bit about the page itself, and then you'll be able to browse tools by category. So at the top, you'll see some charts, and on the upper left, what I'm showing is just the percentages of what tools are available, cell line, animal model, biobank, for example. You can explore the tool metadata, so I encourage you to click a tool, view the metadata associated with that. We recently added more links so that you can kind of navigate to some of those external databases that have a lot more information on like that cell line or antibody. And how all of this relates to LLMs and trying to connect what Janita was talking about to now the NF Tools database is there's a lot of literature out there that has observation data or just all of the results associated with these tools. So what we've added is this ability to add, to show observations. And when I'm saying like an observation, it's something that occurs with the cell line or animal model. So like at X number of weeks, this is what I observed. And what we're trying to do is try to condense that information. And really using large language models seems like a great opportunity to make this happen. So here's some example of observations. And what we also recently implemented is this natural history timeline. And so by kind of like curating this information, we can then put on a timeline of like, from the prenatal stage all the way to the adult stage. So this is in particular for a mouse model. And there's an interactive bar where you can highlight over the observations. So I'm going to shift over to Robert, who's going to really dive into now using the LLMs in order to curate publications. So the main issue we're kind of trying to resolve is, let's say, there's tons of observations out there, and actually last year we went around, really before the hype of AI and all the LLM, things that have been happening, we thought like, okay, we want the community to send us their observations, but in reality, like that is pretty hard to do. You guys have a lot on your plates. So one of the things is like, in order to solve this issue of like researchers don't have time to contribute all the information, but you can send us a lot of like your papers or your lab notes. So that's kind of the idea is like how can we get all this information and then use LLMs. So I'm going to pass it over to Robert, who's going to go into this a little bit more.
Cool. Yeah, so as Christina was mentioning, it's really hard to crowdsource data just because it's really difficult to incentivize people to contribute information. Time is the most precious commodity, and so it's really hard for us to ask you all to say, okay, can you sit down and fill out this Excel spreadsheet that has all of that is asking all of this information of you. And so we thought that a more fluid process for collecting these types of observations about animal models and cell lines would be to resort to large language models. As Christina mentioned, lots of publications. The whole point of publication is to share your observations, and often that is about a cell line or an animal model or some other disease-relevant tool. And so we thought LLMs seem like we could automate this process a little bit with LLMs. And so this is just an example of prompt engineering we use ChatGPT in this case to extract information from a publication. So this is, to tie it back to the concepts that Janita was talking about earlier, this is a combination of prompt engineering and retrieval augmented generation. So we're giving it a PDF and saying, hey, can you tell us about it? Can you pull some of this information? And so in this case, the prompt is, I'm interested in learning more about the mouse models in this manuscript. Please extract a comprehensive list of temporal observations relevant to neurofibromatosis from this publication. Give it access to the publication that describe the natural history model as they relate to development of age. I provide an example, and so this is that few-shot learning that Janita was talking about earlier. So I give it an example of what I consider to be an observation, because it's a bit of an abstract concept, and LLM would not inherently necessarily know that. And this is my formatting preference because I'm trying to get this into a database. But you could say, please format this like a table, or please write the sentence out. So in this case, I'm asking it to assign particular pieces of information to each observation so that we can easily bring it into our database. And so this works. I was a little bit surprised at how easy it was. So for this particular example, we get a couple of observations out. The first observation is a survival rate issue starting at 10 months of age in this particular mouse model. So they begin to die at 10 months of age. And the second observation is that one of the other types of mice that was discussed in this paper has an embryonic lethal phenotype at E13.5. One of the things that I thought was kind of cool is the paper just said E13.5, and somehow the large language model was able to infer that this means it's prenatal and it's at 13.5 days, which I think if you asked a non-scientist, someone who hasn't worked with mouse models, they probably wouldn't know what E13.5 is off the cuff. And so it's doing a lot of the work for us. So instead of us having to read this paper and manually extract and categorize and organize all these observations, we can just run them through a large language model. And I just talked about all of that. So these are the observations. We can go back to the paper for confirmation just to check, is it making stuff up or is this real? And indeed, when you go back to the paper, these two observations that it extracted are bona fide observations that actually exist in the paper. It's not hallucinating. And yeah, so then once we have these, we can add it to the portal, we can throw it on our timeline, and so now you can click on, for example, in this pig model, at 4 months, this NF1 mini pig starts to get cafe au lait macules, and mini pig neurofibromas develop around 4 months of age. And so we can start to assign this information to this natural history timeline. And so that's great. You can plug papers into ChatGPT one at a time, ask it that question, and it's still a pretty manual process that's not automated. And so where we are today is we've recently built a pipeline using Amazon Bedrock, which is a service for deploying large language models kind of in a protected environment. So for example, if you wanted to process electronic health records, this is the type of service you would want to consider using in order to ensure that your data isn't just going into Sam Altman's pocket over at OpenAI, and he all of a sudden has all of your patient information. So in this case, we created a database of NF tool publications. So these are just all the publications that are mentioned in our database. We extracted about 400 of them. We plugged this into what's called a knowledge base that we build in AWS. AWS, or Amazon Web Services, does a lot of the heavy lifting for us, so you kind of plug the PDFs in and you get a knowledge base, which is pretty cool. And then we linked it to a large language model called Claude 3 Sonnet. And so at this stage, that model will receive instructions from either a user or from code, and it will search the knowledge base for relevant information to that query. And then at the very end of the pipeline, we have some Python scripts and things that just kind of help orchestrate all of this and make it happen. So we can just run that Python script and have Claude 3 go through all the tools in our database, go through all the publications in its knowledge base and start to pull things out. And so we actually did this 2 weeks ago now, I think, and we were able to pull out 800 observations from these papers, just kind of in like 5 or 6 hours of hands-off time. It took a fair amount of time to set up the infrastructure, but once we had it running, it was totally hands-off. The other thing that is kind of interesting here is then we could take this knowledge base and actually create a chatbot around it. So we could create a NF Tools chatbot that asks anyone to ask questions about the publications or about the tools in the context of the data portal. So if you are, let's say, looking at a particular tool and you come from the Drosophila field and you don't understand the nomenclature that people are using to describe their mouse models, you can be like, well, what does this mean? Like, why are they describing it this way? And start to get answers in situ in the context of the database when you're looking through it. And so I'm going to shift gears a little bit now and talk about another use case that we're exploring and particularly excited about, and that might be useful to you all as well. And this is making science more accessible. I don't know about you, but the research indicates, and my personal experience indicates, that writing summaries, particularly in plain language, describing your research in a meaningful way is challenging, and it's a skill that takes a lot of work, a lot of time, and it's my assertion, at least in my case, that large language models probably do it better than I can. And so this is something we've been experimenting with and trying to benchmark and quantify. So this is an example abstract. I pulled it out of the NF data portal that, I think if you understand NF1, if you understand how protein variants work and mutations work and some of the jargon of the NF1 field, you can read through it. But if you were to present this to someone on the street, they would not understand what it was talking about. And so we can plug this into a large language model. And my text got really tiny up there in the corner for some reason. But that says, this is the prompt, which is please modify the abstract so that it is 8th grade reading level or 6th grade reading level. And so this works really, really well. We get something like the NF phenotype, which is clinically variable, which, again, if you don't have specific training or background, might not mean a lot to you, to something that is much more digestible to a broader audience. So NF1 is a health condition that can look different in different people. Another example is this section that says, we will test the hypothesis that neurofibromin differentially interacts with binding partners in a cell type specific manner and that those mutations differentially disrupt those interactions. And it translates it to something that's much easier to parse for your average person. So something like, we think that neurofibromin interacts differently with other proteins in different cells and that the gene changes can change those connections. And so you can plug these, both of these abstracts into, this is just in this case Word, where we're pulling out readability statistics. And so one of the common metrics of readability is called the Flesch-Kincaid grade level. And when we pull this out, we put the initial abstract in, which is on the left. We get a grade level of 15.6. And then when we put in the right-hand one, we get a grade level of 9.3, which isn't quite 6th grade level, but it is substantially easier to read. And we've extended this to larger sets of data, so trying to simplify more abstracts that are on the data portal as just an example, and quantify this to see if it's, if this works systematically beyond just that one example that we started out with. And we can see that if we plug in with a target 8th grade reading level or a target 4th grade reading level, we can significantly increase the readability, decrease the complexity of scientific abstracts using large language models. This is another metric of the same thing, that's the opposite direction. So if it gets bigger, that means more readable. And so now it's time to get some hands-on experience with large language models. We have prepared some examples similar to session 1, in which there's just little exercises that you can use with ChatGPT or other large language models if you prefer. And we hope they inspire you to think about some ways that you might apply large language models in your day-to-day work. And so while The examples I've provided up here may not be what you're doing day to day. There probably are ways that you can integrate large language models into your daily work to be more efficient and spend more time doing things that are more important to you. And so we've developed a series of hands-on tasks that you can try to get some experience using large language models if you're totally unfamiliar. Just a couple of notes first. So we prepared 3 workshop tasks. You can select 1, 2, or all 3. I think Christina emailed them out not that long ago, so you should have an email that has links to all of these tasks so you can walk through them easily. If you have a free account for ChatGPT or one of the other large language models, we do suggest doing the tasks in the order of your interest in them, with the most interest first, because a lot of the free accounts do have limits that you'll run into, which will make the exercises difficult if you are not able to use ChatGPT anymore. We tested all of these with GPT-4o, but they should generally work with other current LLMs like Claude Sonnet or Llama. I think an important thing to remember when working with large language models in general is that they sometimes do unpredictable things. I can't tell you the number of times I redid that prompt for extracting observations from PDFs. It seems like something that would be really simple, but I ended up with something that was several paragraphs long, trying to like capture all of the weird things that the large language model would occasionally do, like make up observations or just create dates, create times, things like that. But it's important to remember you're in the driver's seat. You can always engineer your prompt to tell the LLM to do what it's doing a little bit better. And we're happy to help with that. And this would be a good time to log into ChatGPT or your chatbot of choice. So for the first working session exercise, as I mentioned, you can pick one, pick all 3, really is up to you. For the first one, the exercise is to summarize a large block of text from a publication and extract the information that's useful to you. And so hopefully you'll be able to learn to use ChatGPT to effectively summarize text and then extract and retain the information that's most interesting to you. So we have a link in the slides here that you should also have in your email it's a little Word doc that will kind of run you through some suggestions. It has a publication that we've selected for you to start with, although you're welcome to put whatever complex text you'd like in and experiment as you will. For exercise 2, we're going to focus more on extracting and curating data from particular publications. And so we'll learn how to plug in an image to ChatGPT in this case and extract the information from within it. And so your inclination, if you see a table in a publication and it isn't text that you can copy and paste, might be to start transcribing all of that. In this exercise, you'll learn how to use ChatGPT to make that much faster and much less painful. And then in the third exercise, and this might be of particular interest to people that are contributing data to our data portal, we've provided an example and a metadata template. So these are metadata that would be associated with data that you're uploading to a data portal. These metadata manifests are super, super important. They're also super painful to fill out because there's just a lot of information that you have to provide. They're quite complex. And so we've been experimenting with using ChatGPT and other large language models to try and at least semi-automate this process. And so we've put together an exercise to use ChatGPT to extract information from publication or from a method section and semi-automate the process of annotating the metadata. So spending less time doing the painful stuff. These are all 3 working sessions, and I think with that, I guess I'm happy to take any questions before we break out, if there are any. Yeah. Mm-hmm. It's a good and interesting question, and I don't think there's a straightforward answer. There are, looking at what the direction journals are moving in, it seems like they're often saying, do not cite ChatGPT as an author. It is a tool. It did not provide an intellectual contribution. And so I think you're safe not doing it. I do prefer when I'm using ChatGPT, especially because if you're doing this at scale with like, let's say like 30 publications, 40 publications, it can be very difficult to like catch all of the potential errors that it might have made. And so I do like to be transparent that like this has gone through a large language model, like view what you're seeing here with a little bit of scrutiny. So I try to make it transparent, but I don't necessarily like cite it in the formal scientific process sense. Yep.
One of the problems of knowledge maps is it's hard to judge the quality of the publications. And as we know, many publications are wrong, incomplete, or cannot be replicated. So I wonder if there could be a consensus prompt to create like a QC score. So you can then weight the evidence into the QC score, and some papers should be,
Yeah, that's a super interesting idea. I think the direction we focused on now is trying to determine if there's consensus between different publications for observations. But I think it's a really interesting idea. I think the challenging thing is defining the consensus of like what merits a paper that is quality versus not.
at least a couple of papers with a list of terms, list of issues that should be reported, like background screen of the model, or the number of samples that were used for statistics, etc. So using those publications, we get a start.
I'll have to look into that. I appreciate it. Thank you. Hi. I think in the back, yeah.
So you mentioned that the language sometimes can use the information to interpret some results, give you, like when you mentioned the age of the model, for example, it just had 13.3 and it sort of interpreted that. Have you come across over-interpretation? And can you use, you said you also can use your engineering prompts to kind of control for those things that it makes up. Is that a thing that you consider, or?
Yeah, absolutely. In my testing with the model observations in particular, I saw a lot of hallucinated or unconvincing observations that were extracted. And so I went through several rounds of prompt engineering to try and ensure that only the most confident and supported by the text, not necessarily by the evidence in the text, of observations were extracted. So we've leaned very hard towards like, let's eliminate all of the false positives, or as many of them as we can, the hallucinations, and we recognize that we're probably missing some true observations because of that. But I think it's, at this point, just safer to opt in that direction.
My thought was there are certain things that it will be able to extract, but other things, in terms of interpretation, is not quite so simple to kind of cross from, let's say, one model to the other. So I don't know where they are in terms of that kind of challenge of sort of being very specific. Things that are very specific to a particular model or particular source that are so hard to interpret the other.
Yeah, and I think at least for now, we're trying to limit the amount of interpretation that's happening and like really only pull things out that the authors of that piece test. So like we're relying on the author's interpretation more than the LLM because for that exact reason. It's once you let it do whatever, it starts to make stuff up. So. Yep. All right.